All right, next one. This one has a story with it. Now you're going to look at different types of reactions because tomorrow night you have an active chemistry assignment that is on the types of reaction. And I gave you a brief overview when we started talking about the double displacement. So I'm going to go into more detail, except for some of these, I'm just going to say, yeah, we already talked about it. So I won't say too much about our double displacement. But there are, in general, two ways that we describe the types of reactions. And so when you do your homework, sometimes it's talking about one way and sometimes it's talking about the other. So you might look at your choices and you might say, oh, this is a precipitation reaction, but precipitation isn't a choice. So you have to know, oh, a precipitation is a kind of double displacement. And so you'll be looking for that. So the first way is to organize by how many reactants and products. And so we already talked about double displacement. This has another name that is an older name, but you will see this sometimes. I used to include it on my tests. And so if I'm using a question I've used before, sometimes you'll see the word metathesis. So it just means double displacement. This way of organizing, a lot of times you'll hear people talk about it in terms of people going to a dance. So the double displacement is the two couples go to the dance and then they switch partners. So active likes to ask questions. What's the general equation for double displacement or single displacement? So this would be a general equation. What we're looking for when we're determining this is the number of reactants and the number of products. So there are two of each, and they are both ionic, except for neutralization. Sometimes we have water, or we always have water in neutralization, but if our double displacement has a neutralization, it includes water. Okay, so we talked extensively about double displacements. I'm going to go on to the next one. So this is somebody goes to the party alone, sees a couple dancing. B goes off and grabs some punch. By the time B comes back, A is dancing with X. Okay. So we've got B bumped out of the situation and A put in the situation. So we still have two reactants and two products, but the difference is we have elements instead of ionic compounds. So mostly we're counting products, but we do have to pay attention a little bit to what's there. So we have one ionic, or it might be an acid, and one element. And then our products will be one ionic and one element. So we can have two varieties of these. We might have a metal displace a metal. So if you take a piece of aluminum foil and put it into a solution of copper, like copper sulfate or copper chloride, the copper is more attracted to the electrons in aluminum than aluminum is. And so it will gain those electrons and precipitate out as a solid. And the aluminum will get together with the sulfate. Sulfate has a -2 charge. Aluminum always forms a +3 charge. So it's not charge balanced like this. We have to have a couple combined. All right. When we balance these equations, they're going to have coefficients. So if you're counting reactants and products for this purpose, don't worry about if there's a 3 in front or a 2 in front. No matter what the coefficient is in front of this, this counts as one reactant, that counts as one reactant. Okay, the other thing we could do is we could have an acid. So let's say I take that same aluminum and I put it in, what's your favorite acid? Sulfuric acid. The other two classes said hydrochloric, but that's okay, this will work. All right, so the aluminum's going to bump the hydrogen out. We're going to end up with this same product, which is nice that you picked the sulfuric acid. And then instead of a metal, we're going to get hydrogen, and it won't precipitate. It won't be a solid. It will form bubbles and turn into a gas. So you'll do this with, might be magnesium, might be zinc, but you'll do this in lab. It used to be that this was a way of obtaining hydrogen for early chemists. And when lighter than air travel of balloons was used, one of the first things they thought about using was hydrogen. So if you've heard of the Hindenburg, that is a dirigible, which is kind of like a balloon ship, but it's got an engine instead of just a basket or whatever. And it was filled with hydrogen. But they found out that having hydrogen in an environment where maybe somebody lights a cigarette, maybe there's a spark, whatever, that causes fire, and that went down in flames. So not a good idea. Now we have hot air balloons. All right. These reactions don't work in both directions. So if I take a piece of copper, like a penny, and put it in aluminum sulfate, it's not going to go in the other direction. I can't bubble hydrogen through ionic solutions and get the acid and the metal. So we have what's called the activity series. The activity series tells us which direction the reactions will go. So we could spend a lot of time going through, which elements are where. I'm just going to kind of give you three general categories. So we have our group 1 elements. Those elements, if I take the pure element and drop them in water, it doesn't even need to be acidic water, it can just be water. It's going to react and we'll get bubbles. And if it's potassium, we'll get fire. Or if it's rubidium, we'll get fire. And so we'll have a reaction. So group 1 elements displace hydrogen in water and theoretically could displace all other metals. The second category is going to include things like magnesium and calcium, which are a little bit like this, but sometimes you need steam or hot water to get them to work. And then sometimes you need it to be an acid. Okay, so there's like an organization with at the top would be things like aluminum and magnesium and calcium, and then your transition metals would be further down. We're not going to worry about that. So most metals fit into this middle category. And they're going to displace the hydrogen in an acid, but not in cold water. So aluminum is fairly high, and it will displace almost anything else. So I can take a piece of aluminum foil and put it in a solution of pretty much any transition metal, and I'm going to get that transition metal to precipitate out. Below that, we have metals, and there's just a handful of them that don't react with acids. So these three, copper, silver, gold, they are in group 11 on the periodic table, one on top of the other. They're called coinage metals. So you don't want your coins to be reacting with water or even mild acids. So you make them out of things that are not reactive. So our coins are made out of, among other things, copper, silver, and gold. In ancient times, those were the main ones that were used. Also in this category would be platinum and what are called the platinum group elements. And it's not just vertical on that one, that includes some sideways ones as well. Those are the main ones that would fit into that category. So these don't react with acids. In general, there's one acid that they will react with, but not because it's an acid. We'll get to that later. Okay, so if I have any of these in solution, and since silver, gold, and platinum are pretty pricey, that usually means copper. So if I have copper chloride, copper sulfate, copper anything, pretty much any other metal can knock that copper out of the solution. So copper's blue when it's in solution. Any other metal I stick in there, and it's going to precipitate out. All right. So I'm not going to have you predict which goes in which direction, but in your reading and perhaps on active, they might refer to the activity series. And that's what it's talking about, is knowing which is going to react with what. Okay, let's finish off this category. So we're still dealing with organization by the number of reactants, and we looked at 2 reactants and 2 products. The other are the synthesis and decomposition. There's really not much more to say about synthesis. As a reminder, we talked about this also having other names like addition. And it will have 2 reactants and 1 product. It might have 3 reactants and 1 product. So I'm going to put 2 plus. Because it could be 2, could be 3. Theoretically, it could be 5. I've never seen that many. But only 1 product. And that's the key thing you're looking for. If there's only 1 product, automatically it's a synthesis reaction. There is a particular type of synthesis that comes just from the elements. So in theory, we could be combining a compound and a compound or a compound and an element, but if everything is elements, we call it formation. All right, so this is a formation reaction because there is only 1 product. Now notice there's a coefficient in front of here, but there's only 1 chemical in the products, just water, okay? When it comes only from its elements, we can use the energy of that reaction to determine some energetics of what's going on. So when we get to chapter 5, this formation is going to become very important. All right. And then the 4th way of categorizing would be, so these are 2 people that came to the party alone and then they start dancing. Decomposition is the people that break up at the dance or the party. Decomposition reactions, since you don't have 2 things coming together to react, it's just 1 thing. The way that that normally gets started is usually you provide heat. And so you will often see a little triangle. It's supposed to look like a flame drawn under the arrow to indicate, oh, we heated up the reactant, and that's how we got the products. So we could just take a compound and break it down into its elements. So I've got mercury oxide. This is kind of a reddish compound. If I heat it up, I'm going to get mercury liquid, not because it's hot, but because mercury is liquid at room temperature, and it's silvery, and I'll get oxygen gas. Okay, so the key with these is there's only 1 reactant. There are a couple of kinds of compounds that it's pretty easy to predict the kinds of products that you will get. So if you are starting with a hydrate, if you heat it up, you're going to drive off water. So remember, hydrates are the ones that have that dot with the H2O after it. You did this with the magnesium sulfate. You're going to get a compound plus water. And as an example, magnesium sulfate dot 7H2O gives you magnesium sulfate plus H2O. And I realize I'm getting into that hard to read area. Okay, so again, this might look like multiple compounds, but there's no plus. So this is just 1 thing. You had a container that had magnesium sulfate hydrate, and you put it in your crucible. 1 thing you put in your crucible. And then what did you do with it? You heated it up. And then when you heated it up, steam came out. You might have noticed it started to look wet first and then it dried out again. That's the water leaving. And then we had your sulfate. Then the last one, I don't want to get too much over here, but I will put it here. So this fits into the same category of decomposition, is if you have a carbonate or a bicarbonate with hydrogen in front of it, it's going to decompose to form an oxide and CO2. Okay, so carbonate has CO3 at the end of it. The CO2 will come off, leaving behind 1 oxygen. So let's say I had nickel carbonate and I heated it up. then my products would be nickel oxide and CO2. So organize if we're doing combustion reactions. Okay, so type 2, or method 2, I guess, of doing the reactions isn't about how many there are, but what are the types of chemicals. So we have one major group that just doesn't change, and that's our double displacement, but that's where we divide it into the precipitation and the neutralization. So, and I don't know if I said this before, sometimes you see the word metathesis is another name for a double displacement reaction. So this is the method where you really separate into precipitation versus neutralization. But sometimes when people organize these, they just go ahead and do it over there. So the precipitation is 2 ionic goes to 2 ionic, 1 solid. And the neutralization is acid plus base goes to salt plus water. So we talked about this last week. How do we know an acid when we're looking at the chemical formula? Yeah, the hydrogen will almost always be out front. So we mostly look at inorganic acids, hydrogen plus an element, or hydrogen plus an element plus oxygen. So nitric acid, sulfuric acid, chloric acid, those kinds of things. But if we have an organic acid, sometimes they are written as some bunch of carbon-y stuff at the beginning. So that's what R is, and then ending with COOH. So those are acids. Oh, I should write this underneath here. It looks like that's a base. And then our bases are generally going to be a metal plus hydroxide, a metal plus just oxygen, because as soon as it hits water, that oxygen is going to start picking up hydrogens and form a hydroxide, or a metal plus a carbonate or a bicarbonate. And then the salt is the ionic compound, so it's going to be the metal plus whatever is after the hydrogen. But in the case of these last two, you will also have CO2 as a product. So one of the things that you're going to do in lab next week, you're going to do lots of mini little experiments. And one of the experiments is going to have a carbonate, and you'll see some bubbling. So it's a neutralization where you combine the acid and the base, and you get a salt and water, but you also get carbon dioxide. So just a heads up on that one. All right, but there are others, like I said, combustion, that are involved. So if we call precipitation 1, neutralization 2, 3 would be, again, single displacement. It just doesn't really change a whole lot. So we're going to have ionic or acid plus a metal as a reactant. And then 4, combustion. Combustion means there's fire involved. So you're going to have a reaction that is a synthesis reaction, but is also going to be a combustion reaction because it's going to involve fire. Usually oxygen is the reactant, is a reactant. So the common one that we looked at was or organic things. So this is just one of the random facts you need to know. Whenever we burn something organic, if it's got carbon in it, we're going to get carbon dioxide and water as our products. Now, if it also has carbon and nitrogen, for Tuesday. So when you're looking, they do a lot of things that it's single displacement, double displacement. If it's asking if it's oxidation reduction, look and see if there is an element. So anytime we have the single displacement, remember, we're gonna have an element. That's always oxidation reduction. Sometimes our synthesis is, sometimes it's not. All right, Max, I'm really sorry about the connection today. If I can get this to record better later, I will send you a recording of a better version of this. Thank you for this.
No, you're okay. Thank you for everything.